An object 20 millimeters high is placed 50 millimeters away from a convex lens, focal length 20 millimeters. So you measure 2 centimeters, you measure 2 centimeters, you measure 2 centimeters, you measure 2 centimeters, and you then measure 5 centimeters, which will be out around about here. You draw this object and you label it. Sorry, these aren't very accurate on here, but anyway, that object, and you label it O, and it is 20 millimeters high, so it's 2 centimeters high. Then you have to take a ray from the top until it hits the lens. Put an arrow on. Go through F, put an arrow on. Take another one from the top of the object through all the way through M until it crosses. Then you've got an image which is inverted and diminished and real. So determine what are the properties: inverted, diminished, and real. And then it says determine the magnification. So I can't do it perfectly on here, but how would you do it? You would say magnification is image distance over object distance, or image height over object height. So the image distance you would need to measure, and the object distance is 50. Or you could have used the object height, which was 20, and measured the height of the object. Remember, no matter what, this number will be smaller than this number, or this number over here would be smaller than this number. So no matter what, you should land up with a magnification that is less than 1. A postage stamp is 20 millimeters high and it's placed 30 millimeters away from a convex lens of focal length 50 millimeters. So let's just take a look at the picture. This time I have got a focal length of 50, so this is going to be 50, 5 centimeters, 5 centimeters, 5 centimeters, 5 centimeters. And then you can put in your postage stamp 20 millimeters high between F and the lens. And what is going to happen from that is that you are going to land up with rays that diverge apart. So you're going to extend them backwards, and you land up with a virtual image on the same side of the lens that is enlarged. Calculate the magnification. This time you would measure the object distance and the image distance, and you would put image distance over object distance, and you'll get a number much bigger than 1. Or you would have gone image height over object height, and you again would get a number much bigger than 1. Matchstick of length 44 millimeters is placed upright on the principal axis 90 millimeters from a concave lens of focal length. So again, we now need to use a concave lens. So I've got my concave lens. Don't forget to show the arrows. With your convex lens, you would have done the arrows the other way. This time I would have measured 30 millimeters, 30 millimeters, 30 millimeters, 30 millimeters. These are quite kind examples. None of them have really required me to use a scale or to do any unit conversions, but you would perhaps have to do that in a test or an exam. Then you have the length of the matchstick is 44 millimeters, and it has been placed 90 millimeters. So in essence, it's like 3F away, and it's 44 millimeters high. And we're going to call that the object. Then I bring in a ray, and I dot from F, and I diverge it. Don't forget your arrows. And I come from the top through M, and I land up with a weeny teeny little upright image. It's a virtual image, so maybe we must just, there we go, make it like a dotted line. Very difficult to do in this situation, but anyway, there it is. And then you were expected to measure the size of that image. What energy conversion takes place when a film is exposed to light? They're talking about photographic film here. And light, the photons come and they have a chemical reaction. So it's light energy into chemical energy on the film.